Good evening, everyone.
Good evening, sir.
So I guess we can start. Uh, so good Swag Singh, have you read the paper?
Hello.
Oh yeah.
Yes, I did read it.
So okay. Can you please explain your view about the paper?
Okay. So I actually really like this paper from the previous ones, and so this paper actually trying to tackle a specific problem with modern robotics, which is uh, all the neural networks and all the simulation softwares. They are training their robots to a specific robot, right? The algorithms are to a specific robot, not to a, like, it's not generalized. So this is what this paper is trying to tackle. So they are using a architecture called unified robot morphology architecture, and they've actually built a version 2 of it. So in the related works, it says lot of simulation softwares are required to train the robotics algorithm, because you can't just build a robot and then test the algorithm on it in the real world. That would be like really expensive, and it won't be as much iteratable as a simulation environment. But it is also like really slow. So what they did was they are using the embodiment factor, like the robot morphology, the shape of the robot, like how does the robot look. So they are considering it is as a key factor into their architecture. And okay, so they use a lot of like data science terminology in it, which I couldn't quite like understand. So it's a bit advanced for me. So, but I try to understand it as much as possible.
Hmm.
Okay, so yeah, so what they did was in the inputs. So this in the figure 2, they explained the architecture, and they have given 3 inputs. They have classified a robot with 3 inputs: joint observations, joint descriptions, and journal observations. So joint description is basically the description of the different joints in a robot, like how is it rotating, and what is the torque limit on it, and we actually like what kind of a joint is it. So that is like the joint description vector. And in the joint observation, so this is basically describing the behavior of the joint, like the dynamic behavior. So this is so it's like the position and the velocity of the joint. So this is like the dynamic state information. And in the general robot observation, this is like basically the for the information about the whole robot, their gravity vector and their velocity and all that. So these are the three inputs they are using. And so they're giving two of the inputs, the joint observation and joint description, into the joint encoder, which encodes the joint information. And the journal observation input is going into the core network where they train it, I guess, where they train the model. So they have given a mathematical framework on how to encode these two joints vector. And if I go further into core networks, so this is basically the journal observations that like this is the what do you say, the journal position of the whole robot. Yeah, and so all of this is going into the action decoder. Like now, these inputs will go into the core network, and the core network work on it, will work on the joints, and that will then go into the action decoder, which will determine like how the robot will perform according to the joint and according to the position and the velocity of the robot. Like how is it going to behave if a obstacle is there in front of it. So that part will be done by the action decoder. And so they've actually taken a new approach with the action decoder than the first version of the URMA, which is they are like taking the mean value of the joints. They're just taking the dot product. Okay, and if you move on to the embodiment randomization, so this is basically their big breakthrough in the paper. Like, so what they did is, so in the first version of the URMA,
Hi, I'm sorry actually to interrupt. Are you sharing some screen or else you're just not sharing some screen?
no, I'm not sharing anything.
Okay, 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 okay,
You
okay.
can just, I'm just reading it off the paper they provided in the WhatsApp group.
Got it, got it. Okay, I'm
Yeah.
sorry. Yeah.
So in the embodiment randomization, what they did is, so in the first version of the URMA, they used 50 robot bodies, like 50 different kind of robots, and they trained the neural network on that, on just 50 robots. Like they did use the embodiment randomization. So basically, embodiment randomization is like they are actually changing some parameters of the robot, like the length of the robot, their position, the friction of the joints. So all these things, like their PD gains and their IMU position, their motor torque, their velocity. So if you tweak these things, you got a different kind of robot, right? So it won't be the same robot. The neural network you've trained on one robot won't work on the robot that has a different joint friction. So all of these physical limitations, they have increased it when they were training they were training their neural network. They've used like around 10 million of these different embodiments for per training run. So that was a per training run was about 40 hours. And so this is like what they used to journalize the algorithm, so that it can run on any robot. It can run on any robot, right? Okay, so if you guys have any questions, like, you can ask. I mean, yeah. And if I move on to, and also there's a domain randomization also, which is much simpler than embodiment randomization. And one more thing, in this extreme embodiment randomization, in this version 2 of the URMA, they let the neural network know what are the changes in the physical parameters. But in the version 1, they didn't let them know. They didn't let the neural network know. It was like hidden. So yeah. Okay, now if I move on to the performance based curriculum. So in this part, so getting 10 million different embodiments is like really a task intensive on the GPU, and it's like really time consuming. So to increase the performance of their training time, what they did was they introduced a coefficient beta, which is like related to every component, every training component, like domain and embodiment randomization ranges, perturbations, sampling probabilities, terrain attributes, termination conditions, and reward penalty coefficients. So all of these training components are encoded into this single coefficient beta. So basically what they do is, uh, so they are training they are training the robot, right? And if if at one sample, if the robot makes it a successful episode, right? So if it's successful, then they increase the beta. If it's unsuccessful, they decrease it. So for starting, what they do is, let's say there's a simple robot, a four-wheeled car. It's moving on a road. So in the in the starting, there is no other car on the road or no obstacle on the road. So that means like the beta is 0. So if I say, like, if they do 100-meter run, like the car needs to go from 0 to 100 meters. So that is like the first checkpoint. Like they describe it as an episode. So the car goes from 0 to 100 meters. So that is a successful checkpoint. So then what they do is they increase the beta. They introduce some obstacles or some other cars into it, or some other variable, right? And or like they can also increase the speed of the motor or the friction on the tires. Like all these things they can increase, which is just like increasing the beta. So as they keep increasing it, so if it's keep getting successful, they will keep increasing that beta. So that encoding all that information into single coefficient makes it like really performative. And they also show the graphs on that. Like URMA version 2 is like really fast to train. Like not that fast as compared to URMA, but it's a significant increase. But from other simple algorithms like zero padding and multi-head, it's like really fast. Like as you can see, they compare it with the beta. The higher the beta, and the better the algorithm. And they also did some experiment on it too, like the simulation experiment. Like, so Now in the experiment parts, they trained it on 49 robots, and they given that trained algorithm or the trained policy to the 50th robot, which the training algorithm never saw before. So in that sense, like it was like really successful. With the four-legged robot, it was successful, but with the humanoids, they were facing some problems into turning left and right. But going forward and backward, it was okay. But it was a significant improvement from the first version. And then they took that to the real world, and they saw those improvements. Like, I mean, it was like zero shot, right? So the robot, they never trained that algorithm on that robot they tried it on. So it's really impressive that it worked on some of the robots, but they had problems with the humanoids. Yeah. So yeah, that was my understanding of the paper.
Thank you, Gursan
Thank
Singh.
you.
That was really good explanation.
Thank you.
Okay, so moving on to the next person, Santosh. Santosh, are you able to hear me?
Yes,
Okay. So did you go through the paper like which was posted in the group?
not yet. I will check it. Basically,
Okay, no problem.
in the Andhra group,
Yeah.
there's no something like file.
Sorry,
Is it a file? Is it a document file or something?
it's a document file.
No, I can't get anything like that in the group.
I mean, I just posted it on 3rd November.
Well, I just joined yesterday.
Oh, okay, okay.
Can you reshare it?
Yeah, sure. Okay, then the next person, Shivanshu. Oh, okay. Rishwant.
Sorry, I too joined yesterday.
Oh,
After I
okay,
got, I will show.
okay, okay. Gauransh.
Sir, I've also joined yesterday.
Oh, okay. Sanjay.
No, I did not see that this week. I had OPP preparation, so I did not figure.
Okay, no problem. Actually, the to the persons who joined only yesterday, like this is what we do every week. So every week I'll be posting a research paper. So currently the topic is mainly on smart parking, but only this week we just focused on some other paper which is not related to smart parking. And from next week we'll be from this week we'll be continuing again with smart parking. So today I'll be sharing a paper regarding the smart parking topic. So you people can just read it and then just explain your view in the weekend session, which will be conducted every week on either Saturday or Sunday.
Excuse me, sir.
Yeah.
Sir, like then what would happen on like the sessions which would be conducted on Monday?
No, no, no. Only this week, because of the orientation yesterday, it was conducted on Monday. Like it will generally be conducted only on Sundays or Saturdays.
Okay, okay, sir. So like as one of us like just presented in the starting, so like
Hmm.
we have to just present our views on that topic which you are giving us.
Yeah, exactly.
Okay, sir. Thank you, sir.
Yeah. Kapil? Kapil, are you able to hear me?
Oh yeah.
So did you go through the paper that was sent in the group?
क्या?
Did you go through the paper which was sent in the group?
नहीं.
ठीक है, कोई बात नहीं. Okay, I guess
वैसे नीट ये किसके ऊपर है, ये किस टॉपिक पे है?
ये रोबोटिक्स के टॉपिक पे है.
ठीक
ये
है.
पेपर रोबोटिक्स टॉपिक पे है.
मैं तो वैसे ही आ गया था यार, कोई नहीं.
ठीक है, कोई बात नहीं. अगले हफ्ते से उसे थोड़ा पढ़ कर आना, जो भी रिसर्च पेपर मैं ग्रुप में शेयर करूंगा.
ओके ओके.
Okay, guys, I guess that's it for the day. We'll see you next week. Thank you.